Okay, this unit is on sound. So, sound is going to start with a vibration of a material object. So if you're talking about a drum, you're going to vibrate the drum. That will vibrate the air and you will hear the sound. Tuning forks, same idea. The tuning forks will actually vibrate back and forth, move the air, you hear the sound. And it's the same with a guitar string. You pluck it, there is a vibration that will cause the pulse to travel through the air to your ears. Okay. The nature of sound. Sound is a longitudinal wave, so think back to your wave video. It's not transverse, it's longitudinal. And it is created by areas of compressed air, so compressions, and rarefactions. So you have areas where you have compressed air and you have areas where it's spread out. Those are the rarefactions. And there's less air there. It's less compressed. Now, if you look at the little video below and you can see down here the red thing generating a sound wave. It's vibrating back and forth. All right. And by vibrating back and forth, it compresses the air right next to it. But if you look, it looks like the molecules are moving to the right, right? If you look at it, it just kind of looks like they're flowing to the right, but they're not. If you look at one dot, it actually just vibrates back and forth. It doesn't really go anywhere. And that's the difference between sound and wind. The pulse travels from left to right in this video, but each individual molecule basically stays in place. It just does a little vibration back and forth. All right, so demonstration, I'm not doing this demo, but sound is not wind. Sound, you can, when somebody blows on your face, whatever, they blow on your face, that's wind, but you can certainly hear their voice very far away where you're not near them, there's no wind there. The sound is traveling, but the air itself isn't traveling from person to person or from place to place. Okay. Sound does, in fact, need a medium to travel through. Unlike light, light can go through empty space. That's not true for sound. It needs some kind of medium. Now, it can be a gas, it can be a liquid, it can be a solid, but it does need something to travel through. And in fact, we know sound travels better and faster through solids. That's why if you put your ear to the ground, if you're listening for something really far away, people put their ear literally to the ground, the sound will travel further and faster through the ground than it would through the air. So sound travels better through elastic liquids and solids like water and rocks than through air. Now, in water, when you're swimming in water, sound is distorted. It's not the way we're used to hearing it. But it does travel just fine through the water. You can hear things, especially if the sound is created underwater. So we might have trouble hearing somebody talking above a swimming pool. And the reason that is sound doesn't travel very well through different mediums. It's hard for it to go through the air and then into the water. But if you create the sound in the water, it actually travels just fine in water. If you knock on the side of the pool or you make noise underwater, you can hear it. It's distorted and not the way we're used to hearing it, but you can hear it just fine. And the reason sound can travel through solids and liquids is that the atoms are actually closer together than in a gas. Gas are kind of spread apart, and the way sound works is one atom has to vibrate into another, and that creates the pulse, right? Well, in a solid, they're nice and packed close together, so that vibration can travel quite well through a solid. Okay. Now, the reason I don't listen to my own videos half the time is I can't stand the sound of my voice on a video. True for a lot of people, when you hear a recording, you're like, whoa, I don't sound like that. But we're used to hearing the sound of our voice through our skull and flesh and all that, which is a much richer, nicer sound than the sound of our voice through air. Okay. The way the human ear works is you have this little cochlea. That's the little snail thing. You see the little snail? And that little snail actually has fluid in it, and it's the compression of the fluid in there and then there's a nerve ending near there, and that nerve can translate that compression into what we think of as sound. All right, so you don't have to write any of this down, but there's that little snail, the little cochlea, and you actually have fluid compression in there, and then the nerve right up against there will take that and translate that to your brain as a sound. Okay. Now, when we talk about loudness, this is amplitude. This isn't the frequency of a sound wave. This is the amplitude of a sound wave. So, and remember, we can actually diagram longitudinal sound waves by using transverse lines. So if you look here at the two ones, the one on the left is the more quiet sound, and if you look here, you have an area that's not very compressed. So we kind of diagram this going, okay, well, you know, it's not a very big amplitude here. It's just coming up and down a little bit. Then you have a sound wave on the right side over here, and this is loud, and you can see this area is very compressed, and the areas of rarefaction are very uncompressed, and so the amplitude here is much greater. Same frequency, same wavelength, these are just as far apart. There's no difference there. It's the amplitude, the number of compressed molecules, that makes the difference here. Okay, decibels are what we measure loudness in. And decibels are measured in a logarithmic scale, which makes sense because our perception of loudness is logarithmic. So instead of being a linear scale, this is a logarithmic scale, so we're multiplying here. If you're not good with logarithmic scales, there's a really good Khan Academy video. If you put in Khan Academy logarithmic scale, they can really show you that if you're not familiar or you're not good with logarithmic scales. But basically, you're going up by multiplications, okay? So we're multiplying 10 times 10 times 10. We're adding zeros here. We're not going 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 like that. We're actually going to add zeros. And so if we look at these decibels over here on the right, you know, an average decibel of a quiet space, maybe 20 decibels or something like that. And then we go up to a country park is maybe 30 decibels, soft whispers, maybe 40 decibels. And we can go all the way up to levels that where you start to get to painful levels is about 140, which is a jet engine. But near the top, you have a ship's engine room. And when you look at the decibels, that corresponds to the pressure in the air. And that's where we get this logarithmic scale. So if you're looking, and these are in micropascals, and Pascal is just a pressure unit, right? These are going up logarithmically on the right. So it's increasing by a factor of 10 every time we go up our decibel scale. All right, hearing loss. This is by age and sex. So as you get older, you lose your hearing. We tend to lose hearing in the high frequencies first, and this is because the hairs that pick up the high frequency in your ear are the most vulnerable to falling out. So loud music and stuff will cause those to fall out the first. So as we get older, we lose the high frequencies first. So if you take a look over here, you have a male age 60. And in order for him to hear something that's at 6,000 hertz, so that's a high frequency, a high pitch noise, right? It has to be pretty stinking loud for him to hear that, okay? And as you get down to a slightly lower pitch, it doesn't have to be quite as loud for him to hear that, but there's a great discrepancy. Then if you look at a young male, right, going across the board here, he can hear the low sounds just as well or almost just as well as he can hear the high sounds. And what's interesting is here we go, in the area where we speak, down here, this area, we tend to hear, you know, fairly well. Some of the high-pitched sounds get lost as we get older, but, you know, so is life. Okay, the hair cells that line the cochlea are delicate and tend to fall out. So when you blast your loud music, you literally destroy these little hair cells. And once destroyed, they don't get replaced, and then you're deaf. And you're walking around going, what'd you say? What'd you say? What'd you say? Right? And so hair cells that respond to high frequency sounds are vulnerable to destruction. They are the most delicate. And this is, like I said earlier, avoidable like just by not listening to loud music. On the other hand, if you don't care if you're deaf when you're older, go for it. All right. The speed of sound in air. Speed of sound in air is about 340 meters per second. This means that it travels, for a kilometer it's 3 seconds, but it's about 5 seconds to go a mile, and most of us think in miles. So when you see a lightning strike, and remember, seeing is almost instantaneous. So you see it virtually instantaneously, and you want to think about, well, how far away is it? If you can count to 5, like count slowly, 1 Mississippi, 2 Mississippi, that kind of counting. Count to 5, it is 1 mile away. If you got to 10, it would be 2 miles away. Okay. So we all know, I don't think you're not supposed to do this, but we all know that if you suck in helium, your voice sounds like it's higher, all right? And that is because the speed of sound in helium is higher, faster than the speed of sound in air, all right? And then, so you get helium into your vocal cords, and obviously we're not changing the size of your vocal cords. The speed of the sound coming out of your vocal cords is going to be higher, and then when it transfers into the air, we're going to hear that as a higher frequency, which means higher pitch, which is the silly voice you hear. Okay, sound reflects. Sound reflects off of a rigid surface. We just call that an echo. Echo, echo. No, I'm just kidding. So softer surfaces will absorb sound, a hard rigid surface, and it'll bounce off. That means if you don't want sound bouncing all around you, you want to put things that are soft. So why is it quiet after a fresh snowfall? Because that snow is an irregular shape. It's going to absorb the sound, so you're not having sound bouncing around. Same thing in a restaurant. If you look at these two restaurants, you should be able to tell which one will be the quieter restaurant. Okay. Why does singing in the shower sound so good? Well, the reason is that you are having multiple surfaces around you that are hard, and they reflect your sound waves, your song, and they do so just, a second after you say it, not even a second. It's really close to after you say it. And what ends up happening is that each note gets a little smeared. It becomes a little bit longer and a little smoother because it's not that instantaneous when you just say it, it's over. When you say it or sing in the shower, you have that quick echo off of the walls of the shower coming back to your ear, but just a microsecond after you've said it. And it just kind of smooths everything out and makes everyone think that they're awesome singing in the shower. Okay. Refraction. This is different than rarefaction. Okay. Refraction is the bending of sound. Okay. And sound can bend. Light can do this too, but sound can do this because it'll pass through different mediums. So it'll work through cool air or warm air. So if you look at the top diagram here, and you have cool air up here. Well, we know sound travels slower through cool air. It travels faster in warm air. What happens as it travels? Well, it's traveling faster down here and it's traveling slower up here. The end result is it bends up, okay? Or you can reverse that. You have warm air here and cool air here, and it'll travel slower on the bottom part, it'll travel slower up here, and the end result is it bends down. All right, And sometimes you can see this. I live not far off the freeway, or you can hear this. And some days the sound just travels right up and you can hear the freeway loud and clear, and other times you don't hear it at all. And it really depends on the temperature and, other factors, obviously. But one of them is just the direction the sound is traveling. Okay? Ultrasound is just a high frequency sound that we don't hear. And it's useful because it travels through flesh, and we can use that to, see a baby inside the womb or something. And when you're looking at the ultrasound picture, you're basically just looking at the reflection, the echo of the ultrasound off of different medium, and the computer can generate an image using that echo, that bounce back effect. Okay. Forced vibration. Now, if you think of a guitar and you're going to pluck that little tiny string and it's going to vibrate back and forth, and you would hardly hear anything because you're just vibrating a few molecules of air on either side of that string, and you wouldn't be able to really hear it. It would have a very low amplitude. So the way a guitar works is what's called a sounding board. You actually force the guitar itself, the wood and the backboard there, to vibrate when you pluck that string at the same frequency as the string. And then by vibrating a lot more material, you can increase the amplitude of your sound wave. And you can see over here in the picture, there's two different frequencies on these pictures. There's the 553 hertz, and that vibrates a certain section of that sounding board. You can see the areas of vibration, the two lower areas. And then you can see the picture where it's 731 hertz, and that vibrates slightly different areas. And you can also see on that picture, it's kind of cool, that those waves look further spread out there. Right, so you're vibrating that wood a little differently, but by forcing the wood to vibrate, you get a much larger amplitude. Okay. Everything has a natural frequency at which it vibrates. So if you drop a bat on the floor, it makes a certain noise. If you drop a wrench on the floor, it makes a different noise, and it makes your parents go crazy. And then they scream, and they know the difference. You can tell kind of what has fallen, or you can kind of guess the size of what you hear has fallen, because everything has its own natural frequency, and it depends on its size and what material it's made out of and its shape. Okay. Resonance is the ability to force a vibration that matches the object's natural frequency, and the best example of this is a swing. If you kind of get on a swing and you pump your legs with the natural frequency, of that swing, you will, swing just fine. But everyone knows if you do it kind of out of sync with the swing, you'll never get anywhere. And that's because you're not pumping it with the natural frequency. And that has to do with the length of the rope, right? We talk about the amplitude and the period, and that's all the length of the rope. But you learn as a child that there is a certain resonance to this. And the resonance is sort of the minimum amount of energy you have to put in to have this vibration occur. Okay, something that is acoustic resonance is if you have a wine glass or anything, it has its own natural frequency. You can tell its own natural frequency. That's when you kind of wet the rim and you take your finger, go around it. It'll vibrate at its own natural frequency. Well, if you play a note of that exact same frequency, but you do it larger with a greater amplitude, a very loud note, you can break the glass. And the idea with, a really good singer can do this. And the idea there is you can match that frequency exactly with good enough amplitude. You can just break the glass using your own voice. And I guess on Mythbusters, they were able to have average singers break the glass by just using amplifiers, all right? But if you can match the note, the natural frequency that is going to be given off by that glass, and you just do it with a good amplitude, you can get it to resonate and then break. Okay, well, you can do it with glasses. You can also do that with bridges. And the first Tacoma Narrows Bridge, this is up in Washington, was built actually with a very similar design to the Golden Gate Bridge, but with a slightly different natural frequency. Like we said, everything has a natural frequency, so do bridges. And this bridge was destroyed in 1940 by a 40-mile-an-hour wind, which isn't a hurricane, it's just a 40-mile-an-hour wind. It just happened that that 40-mile-an-hour wind matched the frequency and resonated this bridge until it literally fell apart.